Structured backward error for the WKB method. This is a recording of the talk that I'm giving at the CAIMS annual meeting in Regina. The slides are available on my webpage. Please download them. This is joint work with Nick Fillion at Simon Fraser and Michelle Hatzel at Western. So I should begin by announcing Maple Transactions, which is a Diamond class open access journal with no page charges, no fees of any kind. It's supported by the Western Library System and by MapleSoft, but you don't have to use Maple for your papers in Maple Transactions. We're interested in papers that are of interest to the Maple community and that are well written. That's the aim for it. So an exemplary paper is by Richard Brent called Some Instructive Mathematical Errors, and I highly recommend that you read that paper. So the excuse for this talk is that Nick Fillion and I have just published a book called Perturbation Methods Using Backward Error, and you can find it at the Siam bookstore. Much of the material for this talk can be found in chapter 8 of that book. More of the material from this talk can be found at our paper for the Go20 conference in Malta, and that has appeared now or is about to appear in the Springer volume. The design for the cover of the book was chosen from one of the images described in a paper that I wrote with Michelle Hatzel in Maple Transactions. Okay, there must be a few books already on perturbation methods. When Nick and I started the project, we looked and we got 30,000 hits for perturbation methods on Google, and there's more now. So it'd be completely silly to write a book, another book on perturbation methods. Why on earth, right, do it? And so, well, there are only 2 books that we know of that use backward error, and we think it's important to do so. We claim backward error is very useful for perturbation methods, and we think computer algebra is still underutilized for perturbation methods, although there are some works that use it systematically. And of course, there's been some works that have been using it systematically for a long time. And finally, even though scientific computing has progressed far beyond perturbation methods, there is still a need for them. So what's the goal of perturbation method? Perturbation method is successful ideally when you get a short, clear, I say lucid formula that explains what's going on. So numerical solutions and graphs and animations are absolutely valuable, and even so, sometimes a short, lucid formula can tell you just as much as an hour with a simulator and a visualization tool can. This depends on the scientist or the student understanding the terms in the formula, but that goes without saying. I want to preface the talk with a remark about backward error. Backward error is not purely mathematical. And here's a quote from one of the best proponents of backward error analysis, James Wilkinson. He said, although backward analysis is a perfectly straightforward concept, there is strong evidence that a training in classical mathematics leaves one unprepared to adopt it. I have even detected a note of moral disapproval in the attitude of many to its use. And there's a tendency to seek a forward error analysis even when a backward error analysis has been spectacularly successful. Now, I agree with this quote. I've met people to whom backward error analysis seems like cheating. And, well, there's a reason for that, and I'll get into that a little bit. Okay, what is backward error? Backward error can be very easily explained to engineers and physicists and social scientists, lots of scientists, because they're used to making approximations in their models. So formally and abstractly, the job of computation is you've got an input space, you've got data in the input space, and you've got something that you want to compute. You want to compute this y, which is phi of x. Great. For one reason or another, you can't actually do it. Suppose you instead get y hat, okay, and you think of, well, y hat is almost y. That's a forward error kind of conception. But you can also think of it differently. You could say, well, if I had started at x plus delta x with slightly different data, and then I computed phi, then I would have arrived at y hat. There might be multiple choices of delta x for which that was true, of course. Or you can pop up a level and say, oh, I wanted to compute phi, but I really computed this map phi hat, so I changed the model a little bit, and I got my y hat on there. So both delta x and the difference between phi hat and phi are kinds of backward errors. And backward errors need not be unique. But what's interesting about them is that they can help to explain the success of your computation of y hat. You can explain why y hat is actually a good answer. And that's what backward error is all about. It's not mathematics. Of course, it's applied mathematics. But changes in the input data to x plus delta x are perfectly usual in science and engineering, so economics, psychology, anything. Changes in the mathematical model are also usual. One normally neglects terms and effects that are considered to be small or unimportant. One of the goals of applied mathematics is to compute a good model that neglects things that don't matter and concentrates on things that do, so you can understand something about how to control what's going on. All right, so applied mathematicians and scientists are concerned with those things anyway, and they've developed a bunch of tools for dealing with those changes and errors in the models. So if we can put our errors in computational solution in the same context as these kinds of data or modeling errors, then we can reuse those tools. And one of the main ones is the idea of sensitivity or conditioning of the problem. Okay, one particular kind of backward error is called a residual. If we have some approximate solution that's supposed to be an approximate solution S to a problem P of x equals 0, P could be a simple polynomial or some high-dimensional operator. We're searching for something which makes the output 0. Then the residual is what we get when we substitute our putative solution, S, into the problem, P. So R is P of S. Then S is trivially but profoundly the exact solution of P of x minus R equals 0. So a potentially different problem if R is not 0, but potentially just as good a model if R is small as P was for whatever the underlying phenomenon you had. So that's one kind of backward error, just a simple residual. And we'll see another kind, structured backward error. So let's begin with an example. Some physical problems have a natural secular slowly varying term in them. So the aging spring, y double dot plus e to the minus epsilon t times y is equal to 0. So this is like a harmonic oscillator, except that the frequency is varying with time. And we see that it's decaying with time as epsilon is bigger than 0. So as time goes on, the spring gets weaker and weaker and weaker. So Cheng and Mu used the two-scale method to get the approximate solution. Capital Y, which is e to the epsilon t over 4 times sine of 2 times 1 minus e to the minus epsilon t over 2 all divided by epsilon. It's just an ugly solution when you write it out in this flat way. The WKB method, which I will get to, gets this approximation solution directly. It's residual, so you take our putative solution, this ugly formula, differentiate it twice, and you add e to the minus epsilon t times y times that, and you get 1 over 16 epsilon squared e to the epsilon t over 4 sine of blah. Therefore, we have the exact solution to a forced aging spring where the forcing function is r. Is R a small residual? I don't know. It's a bit hard to tell whether that's small or not. But notice that the residual is just epsilon squared over 16 times the putative solution. This means that y of t is the exact solution to y double prime plus e to the minus epsilon squared over 16 times y of t. So that's a problem of the same kind as the one we were trying to solve, with a slightly different varying spring constant. And we can directly interpret that in terms of the original model. So this is what we mean by a structured backward error. So notice that the spring constant becomes exactly 0 when e to the minus epsilon t is epsilon squared over 16. Well, we can solve for t in there, and we can get an exact time at which we get what's called a spurious turning point coming into the solution. And our solution is not physical, beyond that. And Milton Van Dyke, when he discussed the solution, didn't give that exact time. He just said that the solution, the Chang and Wu solution, was valid for t less than order log 1 over epsilon, which is correct, but we have a more precise statement. You can also look at that formula and say, what happens if you change epsilon and you take the derivative with respect to epsilon, you plot the derivative, you see that the solution is actually sensitive to changes in epsilon. So somehow this is a delicate solution, but this is okay because we can see what the delicacy is in the answer. Both of those details matter. Changing e to the minus epsilon t to this thing with a subtracted epsilon squared over 16 introduces a spurious turning point, so likely not physical. The fact that the solution varies strongly when tiny epsilon is changed by even a tinier amount is a kind of ill conditioning. And for both cases, to draw conclusions, we need to know the physical context. We have to leave the mathematics and go back to the original problem. This is a good thing and a bad thing. The mathematics is all about abstraction, and you want to have solutions work in as many contexts as possible. So here we're saying for this one, we've got to go back to what we were actually trying to solve to understand whether we've done well or not. So the important thing is that we've got an answer and a question, and now we can do something with that. And moreover, we identified exactly all of this without knowing the exact solution to the original problem as posed. For this one, we actually could write down the solution in terms of Bessel functions, but we didn't need to. And then there are many cases where you can't write down the exact solution. Okay, WKB and backward error in general. So the WKB method is named for 3 researchers, Wenzel, Kramers, and Bruin. And sometimes the J is added for Jeffries, or sometimes people ignore all 4 of those people and say Liouville and Green did it first, which is correct. Or people abandon names entirely and say, let's just call it a phase integral method. So there are lots and lots of papers and books on this particular method. So for a Schrodinger type equation, epsilon squared y double prime equals q of x y, linear equation with no damping term in there. The method gives the solution YWKB, which is a linear combination of 2 terms, q of x to the minus 1/4 e to the s over epsilon plus q of x to the minus 1/4 times e to the minus s over epsilon, where s is the integral of the square root of q. If you've never seen that before, you look at that and you go, eee. And once you get used to it, it's just amazingly simple. And it's inspired by thinking about an integrating factor for epsilon y prime equals p of x y for the first order equation. This is for q of x bigger than 0, but we can handle q of x less than 0 similarly. Now, in the slides, I have a derivation of the WKB method, and I'm going to skip over that. I'm going to do that in a separate video. I do want to say that you compute the relative residual in the WKB solution, and you just grind it out, and you get the residual divided by WKB is this epsilon squared q double prime over 4q minus 5q prime over 4q squared. And it's a finite formula. It's exact residual. And you see that the residual is proportional to the solution, just like for the aging spring. And this is completely general for Schrodinger type equations. In other words, that gives us the exact solution to a Schrodinger type equation, which has a potential changed by this epsilon squared term. This cannot be a new observation. but we have not seen it in any other textbook or paper. But it seems natural that physicists and engineers and other people who are practically concerned with what's going on would have noticed this, but we haven't seen it written down. And it is a very valuable way of thinking about what the solution has, what the computed solution is. You've got the exact solution to a slightly different problem of the same kind. Great. Once we've got that, we can then say, what is the influence of changing the problem? What is the difference between how much does this change in the problem affect the solution? And it turns out that we know how to deal with this. For linear problems, we've got the whole theory of Green functions to work with. So compute the Green's function for the exact problem that we have solved. Not the one we wanted to solve, but the exact problem that we have solved. And that tells us just as much, because it tells us how sensitive the one we have solved is. So you compute that Green's function, and pretty easy to do that. That's where the pictures on the cover of the book come from. And it turns out, and I don't remember seeing this observation anywhere. I don't remember seeing this observation in the book Bender-Nortzek. Turns out that it's order 1 over epsilon in size. So the forward error will be order epsilon as epsilon goes to 0, not order epsilon squared like the residual. So somehow these problems are sensitive to changes, which is a useful thing to know. And so if you force your Schrodinger equation with noise that's small, it's going to be amplified by a factor of 1 over epsilon. And that's useful to know. All right, I'm going to go on a little tangent here. Another value of computing a residual is you find out if you've actually computed a solution to a problem anything like the one that you wanted to do. And I know of at least 3 examples where people have published perturbation solutions that were wrong. And the first one I will lead with is Morrison's counterexample, published by Bob O'Malley. And Bob O'Malley was a giant of perturbation. Absolutely an expert. Emile Mathieu, in his 1868 paper, made several blunders in his computations, and there's even errors in the venerable textbook Bender-Nortzek, at least in their early editions, and they got fixed in later editions. And I claim that if they had computed a final residual, they would have detected their blunders. Now, given that all of those people are or were experts, and we therefore know that the rest of us make blunders at least as frequently, I claim that residuals are even more necessary for us. Blunder is just an algebraic error mistake, like dropping a factor of 2 or something. To be fair to those people, I'm saying, you made errors, ha ha ha. No, I make errors too. Richard Brent, in his paper that I mentioned before, some instructive mathematical errors, he was fair enough to include some of his own errors in that paper. And so I should say that I make blunders too. I wouldn't be human if I didn't. But to be specific, in my paper with David Jeffrey and Donald Knuth, a sequence of series for the Lambert W function, I claimed that a certain series had infinite radius of convergence. And both of my co-authors said, just okay. I guess I was very convincing, but Richard Crandall later pointed out that I was wrong, and the series had radius of convergence root 2 pi. So blunders are blunders. All right. I'm coming up 20 minutes on this, so I think I will skip iterative WKB, but there's a reason for a way to reuse this knowledge in a neat way. I'm going to could talk about difficulties. The integral of the square root is the bottleneck, and we can use ChebFun to do that, but I think I'll save those for another day. And I'll just end by saying that perturbation is just taking derivatives. You're taking a derivative of the model equation with respect to in a certain direction. And so that's simple. It's a simple idea, but it hides its importance. We're investigating what happens if a small part of the model changes. And of course, that's a fundamental question of science. It's not surprising that the old techniques are still valuable. Maybe it's a surprise just how valuable they can be. But yeah, you can do a lot with a simulation window and a slider bar. So thank you for listening. And this work was supported by NSERC and by the Spanish MICINN, and various universities have supported me for giving visits to give this talk. And both Nick and I thank Stephen Strogatz for his wonderful videos for his course on perturbation methods, especially the videos in which he does the WKB method. If he hadn't done those, we would never have written this chapter of the book or the paper. So I also want to thank him for saying nice things about our book. So thank you for that too. References 1, references 2.